Okay. All right. Okay, so where are we? We're doing this uranium-mediated coupling reaction, and the basic story was that base took the proton, the carboxylate attacked the uranium, HB2 is the name of the molecule. That created leaving group number 1, and then the HOBT attacks and basically kicks everything off, and now we're going to create oxygen, nitrogen, nitrogen, that, okay? So HOBT attacked, kicked this off, and now this is leaving group number, what? So that's the leaving group number 2. So now we basically converted leaving group number 1 over to leaving group number 2. What is the byproduct? What do you think the byproduct of this thing is that came off? Any guesses? Think about just that structure. And it's also a what? 4 letters. Begins with a U. So urea, so it actually created a urea byproduct. This is a very easy urea. It's a very small urea it's actually water soluble and it just goes away. Okay, but now it's all done. And all we have to do is take the amine just comes in. So our nucleophile is NH2 or ethylamine, right? So what's that going to do? Come in, attack, electrons go up, electrons go down, and kick this thing off. See that? Everybody see that? The amine, ethylamine, attacks, electrons go up, electrons go down, thing falls off, and it basically recreates HOBT as a byproduct, okay? Okay, so that's the overall process for this thing called a uranium-mediated coupling. Okay, and these are very common in peptide synthesis. And by doing this leaving group 1, leaving group 2 business, it actually makes a very stable reaction. It avoids like some byproducts and problems that the carbodiimides sometimes cause. All right, so this is a very, very popular method used in peptide synthesis. All right, okay, all right, so let me see. Here's a thought. Here's something to think about. I said that urea is a very stable thing, yeah? Ureas in general. Ureas are super stable, super stable. Super stable. And as just a kind of a finishing thought of this reaction, like if I ask you, what is the driving force of this? Like, why would this happen? Why would you take these things and it comes out with a product? There must be something that drives it, like thermodynamically, right? Something that must make this reaction favorable. Of course, the amide is a nice functional group and everything, but what do you think maybe the thermodynamic driving force might be? Well, I'll just tell you, the formation of a super stable urea. Ureas are very stable. It's a stable functional group, okay? All right. So the driving force is the high stability of the final urea. Driving force. Almost every reaction has some sort of driving force. High stability of resulting urea. Okay, right, and then if we go back, just back to the last page with the carbodiamides, well, they have the same driving force because they also make ureas, right? So the formation of urea is very exothermic. It's very exothermic. Okay, all right, so that's cool. All right, maybe I have just a tiny bit more on this, and then we're gonna move forward. Okay, cool. So number 3, I'm gonna just kind of show in another brief example without going into super detail. There are other coupling agents. That kind of work the same way. And one of them is, I'll just show it, it's called PIBOP. PIBOP. So PIBOP is essentially the same kind of idea, and it's I'll just draw an example reaction of it. Carboxylic acid, OH, H2N. These are a boring example. Simple carboxylic acid, simple amine, simple amide. And we also use triethylamine, ET3N, for the base. And PIBOP, the structure of PIBOP is, it's actually it's a phosphorus-based one, which is kind of cool. So it is P nitrogen, nitrogen, nitrogen. Then it's got that HOBT thing in that we just saw. Nitrogen, nitrogen, nitrogen. HOBT, HOBT. The big difference is it's not based on carbon and like making ureas. It has this thing with a positive charge on phosphorus and an X minus group, another X minus that balances the salt. And to abbreviate this for now, I'm just going to say it does the same kind of thing, where essentially you make R leaving group 1, R leaving group 2, okay. And I'll probably provide a little more detail on this later, but what do you think the first step is? Base takes the proton, right? And then what do you think this leaving group 1 is? Think about what we did before, right? So you take off the proton, you make O minus, right? What's that going to do? It attacks this. It actually just attacks the phosphorus, kicks off HOBT, just like before, right? O minus attacks phosphorus, kicks off HOBT, and that's essentially going to be what leaving group 1 is, yeah? And then you have HOBT, and then that'll attack, same thing, kick off leaving group 1, and then give you leaving group 2, which is essentially HOBT attached. So it's the same exact thing as we just did. HOBT, this crazy big thing is kind of attached. And then finally the amine kicks it off. So all of these kind of work the same way, and it's a cool thing. Used very, very commonly in peptide synthesis, but also like in drug synthesis and just organic synthesis in general. Yeah, all right, cool. So let's end of the tangent. Well, actually, I'm just going to list a couple of these reagents and I'm done. Okay, so these extra ones, the extra ones, they all act kind of the same. You should be able to do the mechanism for all of them, and you'll have a fun opportunity here in a couple homeworks to try this. So there's something called HBTU, which we just saw, HBTU. There's also something called HATU, which is slightly different. These are related. We just showed PIBOP. PIBOP, of course, is this thing. PIBOP, PIBOP, PIBOP. And there's another one called PIAOP. And they all kind of do the same thing. Maybe the last thing I'll show on this tangent here is what's the final byproduct? The final byproduct, is it going to be something stable or not stable? I mean, probably something that's stable, right? Like urea. Ureas are super stable, right? I'll just tell you what the final byproduct is of this. So after all is said and done, base takes proton or carboxylated attacks, kicks this thing off to make leaving group 1. And then HOBT attacks this, HOBT. Kicks off leaving group 1. Now you have HOBT kind of attached, yeah? Leaving group 2. And nitrogen kicks that off. The final byproduct is probably something stable, right? Just like a urea, but there's no urea. This isn't forming urea, but it must be something stable. And I'm just going to close this tangent on this because it's cool. This is the final byproduct. All right, so you may know this, maybe you don't know this. Does anybody know, like, are phosphorus double bond O stable? Is phosphorus double bond O stable? As opposed to like phosphorus single bond O. And like, do you know any biological molecules that generally speaking contain a phosphorus double bond O? So not amino acids or proteins, but other biological molecules like DNA, RNA, right? Of all of our genetic material are kind of linked through phosphate linkages. This is not a phosphate, but it does have the P double bond O, and a P double bond O is super stable. Super stable. Super stable. All right. So yeah, that's basically like in the last reaction, I said, oh yeah, urea forms, and that's the thermodynamic driving force. Well, in PIBOP, which is a cool alternate reagent, that does kind of the same thing. It doesn't make ureas, it makes these kind of phosphorus. I don't have a good name for this with the nitrogens on there. It's kind of like a phosphate, although phosphates have oxygens on here. The big thing though is P double bond O is stable. All right, you can take that home. All right, cool. All right, so we got that. That's it. All right, so we're at the end of the tangent. Maybe a cool little tangent. I don't know. I'm kind of fascinated by this peptide coupling reactions and carbodiamides and oh yeah, one more thing before I go away from PIBOP. One more thing. All right. So we talked about those things called uraniums, right? Uraniums. That was the things that create ureas. This is not a urea. It's a phosphorus stable functional group, right? So if the last thing we talked about were uraniums, any guess what this might be called? It's maybe something else, onium. Something else, onium. Like, what do we want to call it? Not uranium, but maybe something with phosphorus. Any guesses? Phosphorus, something, onium? Make a guess. what is it going to be called? Phosphonium. Phosphonium. Whoops, not phonium. Phosphonium, right? Reagents. And PIBOP is just a classic example of a phosphonium reagent, all right? Good. PIAOP looks very similar also. You can look up, you can Google it if you want. Google it and look at the differences between these. The only difference is the HOBT has like an extra nitrogen in it. And that just actually makes it a little better, although much more expensive. So this is pretty cheap, this is pretty expensive. And the only difference is an extra nitrogen somewhere over here. Okay, cool. All right, so that was the end of the tangent. Let's go back into our antibiotics now. One second. Okay, so we're back into number 6, reactions, carbonyl, enol, and aldol, roughly. And I'm probably just going to start this a little bit, and then I'll just continue in the asynchronous. But we are on E now, which is beta-lactam antibiotics. Beta-lactam antibiotics. So the main derivatives are penicillins, penicillin analogs, and cephalosporin analogs. Cephalosporin analogs, all right? So what are those? I showed you earlier in the PowerPoint. And also, what's a beta-lactam? Anybody want to explain to me what a beta-lactam is? What is a lactam? Definition of lactam, the word. If you had to explain what a lactam is in 2 words. So somebody said antibiotic. Well, yes, these are antibiotics, but I'm asking about the word lactam, because lactam is a chemical term. Lactam. And actually, do you remember lactone? What was lactone? Lactone means, it's 2 words. A lactone is, maybe remember? Lactone. Is a ester, but not just any ester. An ester that is cyclic, a cyclic ester. So a lactone is a cyclic ester. A lactam is a cyclic what? Am. So somebody said amine, and then somebody said amide, and the correct is correct. Yes, an amide. It's a cyclic. A lactam is a cyclic amide. So I could draw the same kind of like this. That would be a cyclic. This is an example of a lactam, but this is not a beta lactam. This is a, so what does the beta mean? Beta. So this is actually a, so the, the alpha beta nomenclature. This is the alpha carbon, this is the beta carbon, this is the gamma carbon, and then we have like delta, alpha, beta, gamma, delta, epsilon. So this is actually technically a gamma lactam. So what would a beta lactam be? Beta is kind of like a different ring size. What's the ring size of a beta lactam? Not 5, but It's kind of like if the beta carbon is directly attached to nitrogen, if the beta carbon is directly attached, then the ring size is what? 1, 2, 3, 4. It's a 4-member ring, right? And that's all the beta lactams are at 4-member rings. So beta lactam. So there's a gamma lactam. Sorry, let's change this around a bit. Okay, so nitrogen. All of them have this 4-member ring with the nitrogen like that. It's a cyclic amide. A cyclic amide. That has a 4-member ring like that. All right, that's the definition of beta lactams. All right, cool. We're cool with that? Okay, now what's so cool about this and these crazy molecules is that they're synthesized super easily, which is fun. Okay. Let me see here. You know, I think I'm because it's kind of a big topic. I'm just going to stop now, and I'm going to do this all in the asynchronous. Or maybe I'll show one example, and then we'll stop. Right? I'll show one example, then we're going to continue in the asynchronous. All right. So let's show a synthesis of one of these penicillin derivatives, and then I'll probably stop. Okay, so let's draw one. These are really easy. It's super easy chemistry. So let's draw this one. Okay, so this is the molecule. Okay, there's our lactam, our beta lactam, right? Sulfur. Methyl. Okay, so this is called benzyl penicillin. Let me check something real quick. Okay, cool. Yeah, so it's funny because not penicillin, it's penicillin. That's nice. Penicillin. All right. Benzyl penicillin. Benzyl penicillin. The funny thing is, I had to double check it. This is a misuse of the word benzyl, because as chemists, we should know what benzyl means. Does anybody know what benzyl usually means? So if I ask you what benzyl bromide is, like benzyl bromide, does anybody know what that is? Benzyl bromide. Definition of what is it? It's, you might say benzene, right? Benzene bromide or something, right? But the definition of benzyl is actually benzene. But actually, yeah, maybe this is right. All right. Benzyl is phenyl, yeah, phenyl CH2 and then something. I guess for a second I didn't like the use of benzyl here, but although that is technically benzyl, that's the correct use of benzyl. All right, never mind. I was going crazy for a second. So benzyl is phenyl CH2, right? And then this is the penicillin scaffold. All right, good. Okay, so yeah, I take back my concern. How do you make it? Well, it's so easy. You can start. All they're going to do is make this bond right here. That little bond, that amide linkage right there. And so they're going to use the acid chloride and then the amine. Okay, and a base. What base do they use? Maybe triethylamine or something like that. And this actually directly builds it in a single step, which is super cool. And what's also cool, this stuff is a very, very simple building block. It's called 6-amino penicillinic acid. Penicillinic acid. 6-amino penicillinic acid, or 6-APA. Is dirt cheap. It's 50 grams for about $140. That may not seem tremendously cheap, although you guys don't all probably don't really know chemical prices. But for a complicated molecule with chiral centers and stuff, 50 grams is actually a ton of material. And for $140, that's actually pretty cheap. I did forget stereochemistry. So the big stereochemistry I forgot is the nitrogen is coming towards us, and also this one is coming towards us. Okay. Anything else? Of course, there's how many chiral centers are there total? Well, that's a chiral center. That's a chiral center. That's a chiral center. So it actually has it's a molecule of 3 chiral centers for relatively cheap. Okay, and I think I am going to stop here. Actually, I'm just going to draw a cephalosporin just for comparison, and then I'll stop, right? And then I'll continue in the other in the asynchronous one, right? Because penicillins and cephalosporins are similar, but they have a key structural difference. So let's just draw that, and then we're done. All right. So it's also beta-lactam. It's also got a sulfur, but it's a 6-member ring, and it's got a double bond, CO2H. Okay. Nitrogen. Amide. This is an example. That's a sulfur up top here. Okay, and this molecule is called Cephaloden. And well, I'll basically continue in the asynchronous lecture, because it can also be built from a key dirt sheet building block through the formation of this bond. And the molecule name for this is called 7-ACA. 7-ACA. So depending on if you use 6-APA or 7-ACA, you can build almost any penicillin or almost any cephalosporin in a single step. The key difference again in the structures is a 5-member ring with a sulfur versus a 6-member ring with a sulfur. But those will, they're both antibiotics. And some of these variations are better for gram-negative or gram-positive bacteria, and I'll talk about that a little bit later also in the follow-up lecture. Is that it? I think I'm done. I think I'm a little over time also. All right. Any questions on this before I let you go? I will tell you one thing that I think is pretty cool. Did they have a protecting group on the acid? Is that protected or no? It looks unprotected, right? How can you do a reaction with 2 functional groups and only work on one of those functional groups? And the answer is You don't really need a protecting group on the acid. It just this happens to work fine. And somebody said because of the stereochemistry. It's not really the stereochemistry. It is it's just the fact that that's reactive, that's not really reactive, right? And because of that, you have two reactive things that do what you want, and the other thing just goes along for the ride. So the carboxylic acid, you don't have to protect it. If you wanted to protect it, you could maybe make an ester, like a methyl ester or something, and then take off the ester, right? That's a common way to protect an acid. Yeah, but anyway, it's pretty cool. You don't actually need to protect this. Okay, any last questions? Stereochemistry, I just realized is wrong. it's a right, undefined. It's a wedge also. So that nitrogen up there is always wedged out. Okay, are we cool? And yeah, I'm going to be posting the homework assignment before I go on my trip on Friday morning. So probably Thursday night latest. All right. See you guys. Bye-bye. Sorry for the technical difficulties.